Hi everyone, this is Professor Karagolian. This video is going to be our last lecture for our lab section. It's going to cover conformational analysis, which is our stereochemistry part 2. I'm going to do a brief review from stereochemistry part 1. If you guys remember, we had the eclipsed, gauche, and anti, and each one has a different degree of angle. What we did was we saw on our sawhorse formula that the eclipse is completely lined up, so it has a 0-degree angle, and then when you move 60 degrees we get our gauche, and then 180 degrees is our anti. The top view here is our Newman projection. So to go into deeper information on that, what we do is we view from the first carbon, and then the second carbon is towards the back. So when you see here the circle, we have the circle here, and then here is our first carbon. Behind that, you guys see how these edges are short line? That's showing the second half. So the circle is this part, and then the dash parts are here. This carbon you don't see from this point of view, but you know it's in the back. This is called the Newman projection. A lot of times when we're showing Newman projections, we don't actually show what's coming towards us, what's going away from us. So if you look at this example here on the eclipsed, the hydrogen and the chlorine are coming towards us. The two hydrogens on the top are in line of the paper, and the two hydrogens on the bottom are going away from us. But you see that everything is lined up, right? So it's a 0-degree change. So that's why we have an eclipse here. So the two hydrogens are very near. So this is showing the 0-degree change. And then on this side, if you look at the staggered, you see how this hydrogen and the chlorine that are coming towards us, but it is kinked. It is rotated around this carbon atom, so it's rotated. So that's how we view this Newman projection. They're more spread out, and because they're more spread out, they're more stable. So when we have clusters together, our molecule is not going to be stable. Here is an example that was covered in your lecture. I'm not going to go over this example. I'm just going to point something out so you know for your assignment packet. Your cyclohexane ring here is denoted by the pH. So you see here we got the pHs. So those are the two cyclohexane rings. I believe there's few problems on the packet that have this, so you can just draw your Newman projection with the pHs. As I mentioned before, these two pHs are on the same side, so they're scattered. They're not scattered. Therefore, these are less stable. These are scattered, so they're more stable. They're on the opposite side of each other. Okay, so when the methyl groups are too close, like in gauche, they will create steric strain. This was covered in your lecture section. So they can also create torsional strain and angle strain. So I put the definitions here for you to refer back to if you need them. Next we have our drawing of the chair conformations. What you have to remember is every line has a parallel line. So any line that you draw has to have a parallel line. So if you draw the middle first, you draw the parallel to it. If you drew this first, this 1 to 2 bond, then you have your 4 to 5 parallel to it. You guys see that? If you drew 6 to 1, then you have 4 to 3 parallel to it. So every line that you draw is going to have a parallel to it. A lot of times when you get used to drawing these, you can just do it in one trial. You don't have to do the 2 parallel lines. So this is how you learn to draw. But if you can just do it in one shot. Okay, my angles didn't match up, but you guys can practice that on paper. It's a lot easier than writing on the screen. So we have our axial bonds, and those are vertically aligned. So either they go up or down. So how I imagine this is that the points that are up, right? So we have our 1, 3, 5. Those get a line going up. The points that are down, so 4, 6, and 2, get the line going down. And then if you flip the ring, it's the same thing. I mean, it's flipped, but it's the same concept. On the other hand, equatorial bonds are different. These bonds are parallel to two carbon-carbon bonds, one bond away. So you have to remember it has to line up with one of the lines on your drawing. So I actually drew out each one by one for you here. So if you have a parallel line 5, 6, and 3, 2, it's going to follow that. You guys see how 1 and 4 are parallel to 5, 6, and 3, 2. And same when you flip it over. And then if you have parallel of 1, 2, and 4, 5, then 6 will be parallel to that, and 3 will be parallel. And then when you flip the ring, it'll be the same concept. And lastly, if you have a parallel line of 1, 6, and 3, 4, 2 and 5 will follow that. So if you flip the ring, the 3 and 6 will follow. So everything is flipped on the right side. Here is another example from your lecture. It's a conformational analysis of methyl cyclohexane. So here we have the 2,1,3 diaxial interactions. That is shown here by the 2 bonds, the purple bond and the red line. So those interactions are taking place. That's why it's 2,1,3 diaxial. If you check on the other side, we have 0 because the hydrogens aren't having any interactions. So here in blue it says up bond. So the up bond is either going the hydrogen, oh sorry, it's for this hydrogen that is going up, this one. So for conformational analysis of cis 1,4 dimethyl cyclohexane, so we have two groups on the same side. So either both have to be up or both have to be down. So I drew the two here for you. So one is, both of them are dashed, and the other one, both of them are wedge. So we can say the dash is, both. It depends how you look on the molecule, because you can flip it over. So either both of them, they both have to match. So if it's cis, remember it's the same. That's how I remember it. Cis, same. So they're both the same. So either both are up or both are down. And this is the example you guys did in the class. So it's showing how both of them are up in this example. For both of these, you have two 1,3 diaxyl interactions. Therefore, it is equal in both forms. It's stable in both forms. I forgot to mention for this, it favors the 0 1,3 diaxyl interactions, because here you're getting that cluster stuff, so you want to have the least amount of that, because this is not stable. And then we have our conformational analysis of trans 1,4 dimethyl cyclohexane. So now it's trans. Remember, trans is different side. So cis, same side, trans, different sides. So now we have our two groups on the opposite. So one is dashed line and one is a wedge line. So one is going down and one is going up. And you can see that in the example you guys did in class. So when you have this first way, you guys see that we have four 1,3 diaxyl interactions. And how do you see that? So I actually attached this image here. If you draw out, so our example up here is for 1,4, and this one is 1,3. Okay, so we see that here how there is multiple hydrogen interactions, right? That's where you get this 4, because you have the 4 hydrogen interacting. So for our bottom example here, remember that this one has a hydrogen too. So you got the 4 hydrogen interactions. And then when you you flip the ring, you see that less hydrogens are interacting, so therefore the flipped ring is more stable. Same with the example you did in class. The hydrogens are not interacting. You have 0 1,3 diaxyl interactions. Therefore, this form of the conformation is more favored. It's more stable. Last note here, remember that the less number of diaxyl interactions are more favored. So if you have, let's say, 3 and you have 1, remember that 1 is more favored. If you have 4 and 3, 3 is more favored. But if they are both the same, then they will be present in equal forms. If you have 2 and 2, then they're both, favored. If you have 1 and 1, they're both favored. So this will help you with the packet. Some of the problems I actually have here are problems of the packet. So if you can just refer to my notes and answer the packet questions. There's a section in the back of the packet that covers the Newman projection. So remember that your benzene ring is denoted by the pH. If you guys have any questions, please email me and I will get back to you as soon as I can. And thank you very much for being so understanding today. And my apologies in advance. Next week, we will do a brief review for the final exam. our final exam is going to be online on Canvas. It will pop up on the home page. If any case you can't locate it, it would be under the quizzes tab. Lastly, I just want to thank you again for being so understanding today, and I'll see you guys next week.